Okay, so how do you go about solving your equilibrium equations to get a equilibrium distribution from a discrete time Markov chain? So I'll start by looking at the finite case. So in this scenario, we have a finite number of states. So in that case, you're going to have n linear equations in n unknowns. And the unknowns that we're interested in are the pi j's. So that's the long-term probability of being in state j. J goes now from 1 to n. And because of the nature of these, one will always be redundant. So we don't quite have enough equations. But we have as well what we call the normalizing equation. We know that the probability of all these states sums to 1. So we can use that. So I'm going to show how you do this by looking at a finite queue. So we've got a queue, and S will be the number of people in this queue, and you can have an empty queue, 0, and it go all the way up to n. Maybe there's not enough room, and beyond that they just don't join the queue. And we're going to have the probability of a person entering the queue, so the probability of it going from I to I plus 1 is P. The probability of someone leaving the queue, that is they've been served. The probability of going from I to I minus 1 is Q. And that's fine except for the boundary conditions. We've got two boundary conditions. First of all, we're going to say that the probability of a queue having 0 people and in one time step staying with 0 people is going to be 1 minus P. And the probability of it being full and staying full is 1 minus Q. So here's our queue. You can see again we've got the circles indicate our number of people in the queue. And you see that it can increase by probability P. It can decrease by probability Q, but then we have the fact that it could stay the same, and for all the states except for 0 and n, this is 1 minus P minus Q, and if you look at this, you'll notice that the arrows that lead out of every state always add to 1. For 0, the probability you stay at 0 is 1 minus P, and if you go right to the far right, the n, the probability you stay a full Q is 1 minus Q. So let's look at our equilibrium equations. So first of all, we can say, well, what is the probability? How do I get to state 0? Well, either there could have been one person in the queue and they could have left, or there was no people in the queue and we stayed like that, no one entered. The same for the pi n. We've got a full queue. We can either have had one person under full queue, so we had n minus 1 and someone arrived, or we already had a full queue and it increased by 1. So the 901 now is, let's think about all the states that are not 0 or n, or pi I. Well, how can I get to state pi I? How can I get to state I? Well, either I could have one more person than that and they left. I could have one person less than that and someone arrived. Or I could have been at the last time point, have I people in this queue and nothing changed. So what we're going to do is we're going to solve these equations. So first thing we're going to do is we're going to look at that first pi 0. So we've got that pi 0 equals pi 1 q plus pi 0, 1 minus p. So that's our boundary equation. And I can rearrange that and I could get that pi 1 equals p pi 0 over q. Right, let's use the equation that is in I and work out what pi 1 would be using that equation. Well, that could be had two people in and someone left, plus the 1 minus P minus Q. I could have had one person in the queue and nothing changed, or we could have no one in the queue and someone arrived. So I can rearrange that and get that Q pi 2 equals P plus Q. Now, I can also substitute in pi 1 by using this equation here. So that is pi 1, so we can rearrange that and write that as P pi 0 over q minus p pi 0. So all I've done there is I've rearranged, I've taken it, so I've got the pi 2 on this side, I've got everything else on this side, and then I've substituted in where I had this, so I've got this final thing. We can simplify that. That is going to be q pi 2 equals p squared plus pq all over q p0 minus p pi 0. And if I rearrange that, I will get pi 2 equals p squared over q squared pi 0. Which we could write as p over q squared pi 0. So we've got pi 2 in terms of pi 1. We've already got pi 1 in terms of pi 2. And in fact, you could actually go and look at the ith case, and I'm not going to go through the details, but eventually you could show that pi I equals p over q I pi 0. So all our states are in terms of pi 0. So now I need to actually simplify this and work out, well, what's pi 0 going to be? Well, first of all, we can use our normalizing constraint or normalizing equation. So we know that pi I, the summation as I goes from 0 to n, equals 1. So let's substitute that in. We're going to get I equals 0 to n, p over q to the I pi 0 equals 1. So that's going to be pi 0. The summation as I goes from 0 to n, p over q I equals 1. Well, if you go back and have a look, you can actually write that summation as pi 0, 1 minus p on q to the n plus 1 over 1 minus p over q. That equals 0. If I've written that right, let me just check my notes. Yes. So what does that mean? That means that pi 0 equals 1 minus p over q over 1 minus p over q n plus 1. So we can now, by taking this and putting them together, we can get that pi I equals 1 minus p on q over 1 minus p on q to n plus 1 p over q to the I. And obviously, if we actually observe this matrix and we had our p and q, we could substitute in and get all our states. The other thing is, I mean, that's one way of doing it analytically. The other thing is, you actually, if you look at this problem, which is we basically have something that's pi equals pi p. Well, the other way you could get this is you could look at the left eigenvalues, eigenvectors, and find the vector that's associated with the eigenvalue of 1. I'm going to do that here, but if you're interested in doing that, if you go and look at the handout, you will see that in the handout there's some R code showing that we get the same answer. Okay, so that's it. That's how one of the ways that you could solve a discrete time Markov chain which has a finite number of states. See you next time.